Hello everyone, my name is Antolin. In this video, I'm presenting my final project for the class Deep Learning at Harvard Extension School. The title of my project is a multi-class text classification performance comparison of classical machine learning versus deep learning models using the 20 Newsgroups datasets. Text classification is the task of assigning predefined categories to textual documents. Therefore, it's just another classification problem that can be therefore classified in different types depending on the cardinality of the labels per document. The typical could be a binary classification if the document is classified as only two categories that are mutually exclusive. The typical example would be an spam detection. A multi-class would be the case where a document can be classified as multiple categories which are mutually exclusive, as in an example like you want to detect the language of a document when you consider only one language per document. There are another case that is the multi-label, where the same document can be classified, can be assigned different categories or groups. Okay, so the goal of this project is to compare the performance of multiple models on a multi-class text classification task using the 20 Newsgroups datasets that is currently available in the sci-kit Learn library. So, and that performance comparison is going to be done by comparing both classical machine learning models and also deep neural networks. In the illustration, I saw what is this an example of this multi-class classification where you input a text, in this case correspond to a post about hockey, and then a multi-class classification system will analyze that text and output one label, and in this case is correctly classified as hockey. So the 20 Newsgroups dataset is available in scikit-learn. So the dataset will be downloaded directly in the code that has been provided, so no extra steps are needed, which is very convenient. These datasets comprise around 18,000 newsgroup posts on 20 topics. However, for the proposed solution in this project, we have restricted that to around 12,800 posts on the following 12 topics: hockey, hardware, electronics, script, medicines, motorcycles, auto, computer graphics, space, for sale, baseball, software, and religion. And as you can see in the chart, those different categories are well balanced among the different topics. So the algorithms that are going to be benchmarked has been implemented using both scikit-learn and Keras. 4 classical machine learning models has been implemented: logistic regression, support vector machine, multinomial naive bayes, and random forest. Additionally, 3 neural network models have also been tested: multi-layer perceptron, the most classical feed-forward artificial neural network, a convolutional neural network with and without pre-trained work embeddings, and LSTM networks with pre-trained word embeddings. To evaluate all these models, accuracy is going to be used as the metric to compare them. Accuracy defined as percentage of correct classifications. This is a commonly used metric, and given the relative balance of our datasets, is a good metric to optimize for and to use for comparisons. Another variable that we're going to use to compare the different models is the time taken to train the models. Additionally, we'll also compute the confusion metric as a good visualization to see where the errors happen. As it should be, like, we are going to split the original data sets in a train set that with 2/3 of the samples and a test set with 1/3. All the tests are going to be done, like the evaluation of the performance of the models are going to be done only on the test sets, and that split is consistent across all the different models. So all the different models use the same train set and the same test set. Only in the case of neural networks, we are going to also use a validation set to perform hyperparameter optimization. Regarding technology, this demo has been developed and tested using Colab, using Colab running on Python 3 and a GPU runtime. So no pre-installation is needed. You just need to take the Colab notebook that I provide, upload it to Drive, open in Colab, and then connect to runtime, as I saw in the slide, that correspond to Python 3 GPU, save, and then run. In case you want to run the notebook locally, you need the configuration I mentioned in the slide: Python version 3.6, Pandas, scikit-learn, NumPy, SciFi, Matplotlib, Keras, and TensorFlow. Okay, so I'm gonna give a bit more details about the implementation of these different models, starting with the classical machine learning models. So as we know, the text need to be pre-processed and transformed before being used by the ML model. This is the transformation that is done is just input the text and you get as an output a feature vector. It's a list of numerical values representing some of the text characteristics. For the classical machine learning models, a bag of words model is used where for each document, a post in our case, the frequency of the words is the frequency of each of the words is considered, but not the order in which they occur. What happens is, like, for each word we compute a statistic that is called the term frequency inverse document frequency, that basically represent the word's importance in each post. So these statistics take also into account the frequency of that word across the whole all documents, so minimizing therefore the effect of stop words such as pronouns or other domain specific language that doesn't add much information. So after pre-processing our 12,800 posts, those posts are now represented by approximately 31,000 features, where each feature is represented with the TF-IDF score using both unigrams, so single words, and bigrams, two words combined. So in this slide, I saw briefly how the different classical machine learning model is implemented using the scikit-learn pipeline. As you can see, the snippet is pretty simple, and you just need to change the model for each of the different 4 implemented logistic regressions, support vector machine, multinomial, naive Bayes, or random forest. The result that you will get by running that code looks like this. So you will get the different statistics like precision, recall, F1 score for all the different classes, the overall precision accuracy score, that is 80% in this case of the logistic regression, and the confusion metrics that tell you where most of the errors happen. Like, for example, autos is frequently mistaken with motorcycles. The best model is logistic regression, as you can see in the table, followed closely by support vector machine. In terms of training time, those models are pretty fast. Now let's discuss a little bit the implementation of the neural network models. Those models also require some pre-processing. In this case, what is done is the text transformed in a feature vector. So basically, for the multi-layer perceptron, the top 30 keywords in all documents are going to be used, and then one hot encoder is computed, as is shown in the slide. So this is the inputs of the multi-layer perceptron. In the case of the convolution neural networks and the LSTM, those models require sequences. So the text is converted in sequence like this with features, a sequence of features where each of these features represent different words. In terms of implementations of the neural network models, Keras has been used. In this slide, you can see all the different configuration that has been tested. As I mentioned before, a multi-layer perceptron has been used, which is just basically the most simple case, but also convolutional neural network with and without pre-trained embeddings has also been tested. In the pre-trained embeddings are used the GLOB, the one provided by the GLOB project. And finally, also an LSTM network with pre-trained embedding has also been tested. In terms of result, the result provided in the notebooks and in the report looks like this. So basically, we compute the evolution of the model accuracy and the model loss through epochs to understand when there is overfitting, potential causes of overfitting. We also output the accuracy score in the test set and the confusion metric as before. So in summary, a summary of the results, what we have seen is like the classical methods like support vector machine and logistic regression gets a really good performance, as you can see in the chart, with around 80% of test accuracy. Only the multi-layer perceptron gets a little bit better performance with 81%, but with the cons of a longer time to train, around 12 seconds in comparison with the 4-2 seconds of the other models. The other, we have also seen that using pre-trained word embeddings improved the performance of the convolutional neural networks, both in terms of accuracy, 70% versus 70% versus 59%, and also in terms of training time, 70 seconds versus 175 seconds. The more complex deep neural network have a worse performance than the classical algorithms. The main reason, or one possible explanation for that, is that these pre-trained embeddings are not trained against the text in the same context. GLOB is based on Wikipedia articles, while this dataset is based on website posts. As a result, for example, we have observed that there are only around 25,000 common words between GLOB and the training sets. That number compared with the approximately 31,000 features, including unigram and bigram, used by the bag of words model. So the combination of more trainable parameters and 30% fewer features might explain why these more complex algorithms have a worse performance than the winning logistic regression, SVM, support vector machine, or multi-layer perceptron. As a potential next steps, I would like to, if I have time, I would dedicate more time in more interactions on the specific network configuration and hyperparameters of the more complex deep neural networks, as this might improve their performance. Another possibility is also to test other pre-trained embeddings that are maybe trained in contexts that may be closer to the one used. That could also help to improve the performance. And finally, another option would be to build your own embeddings for this particular context. That will take a bit more time, but probably will help also to improve the performance. Here at the end, I would like to include some references of all the different demos and demos that I've used to build this to do this final project. We thank you very much. This has been really fun.